The control model is a way of structuring an application into smaller modular entities. The key components of it are control points, which are named stages in the application flow. And then each of those stages can have functions associated with it, which are called actions. At this point, we're still talking sequential structure. So this is the sequential backbone of a parallel application. So when we talk about actions, those are not tasks, and the distinction being that these actions run sequentially, whereas tasks, which you'll see in a future module, are where we get the parallelism from. So why do we have a sequential component of a parallel runtime system? And the answer is that it simplifies the addition and removal of work in this overall structure. So think of the case where you have a large number of developers working on an application. You want it to be modular enough that a new developer can come along and add some core structure to the application without affecting any of the existing structures of the application. So that's what the control model enables, this ability to have multiple developers collaborate on this sequential structure. So the first part of the control model is main, which, as I had mentioned earlier, is replicated across processes, just like main in an MPI program. Then a number of control points are defined under these, which identify the high-level stages. They execute sequentially, but they could have cycles in them, and I'll talk about that more in a moment. So here we have a control flow graph. Then we attach actions to the control flow graph. So you could say action 1 belongs to control point 1, action 2, 3, 4, and 5 belong to control point 2, and so forth. The actions form a directed acyclic graph. So they're executed in an arbitrary order, first honoring the control point order, and second, a topological sort of the DAG. But remember, it's still being done sequentially. This is just a way of structuring an application where a new developer could come along and say, I have a new action, A10, and A10 could run anytime after A4. And I'll show you how to do that in a moment. After the control model, what we'll talk about later in more detail is the execution model, where the actions can launch tasks. A task is work that's distributed over the system, over multiple nodes, and is working on data that also are distributed across multiple nodes. The tasks are composed of multiple point tasks, where a point task is a piece of the execution that's working on local data, which is a local subset of this big distributed data. And again, you'll see later how dependency analysis enables the tasks to be executed concurrently. And this is instead of explicit communication like you would have in a system like MPI. Now, the point tasks have their piece of the distributed data structure, but even though this is already a parallel execution, they might want to execute just that data in a parallel format, and that's where kernels come in. So kernels execute on the local data in a data parallel format to give that additional level of parallelism. So here's what all the parts of FleCSI look like together. We have main in the runtime model. The control model has control points and actions. The actions are the gateway to the execution model, where they spawn tasks, which are made up of point tasks and that launch kernels. And then all of this runs on distributed heterogeneous hardware. So here we'll define a simple control model. It'll look a lot like what will be used in the hands-on exercise, but this is more notional, so it's not an exact match to what you'll be working on in a moment. In this example, we'll define 4 control points: initialize, advance, analyze, and finalize. So we start by declaring an enumerated type. Here we're calling it CP that contains those four. And then it's also possible to declare a function that maps from those symbols to strings, which is used for error checking and debugging and tracing. So to implement this control model in FleCSI, we want something that looks like what's shown in the upper right, where we'll have a cycle where the simulation will advance the simulation, analyze the result, advance, analyze a few times. For simplicity, here we'll do it a fixed 5 times. So we declare a function, here it's called cycle control, that's given a policy, which is an aggregation of the data that it needs. And we're going to say that supposing we've declared a step method there, we'll increment the step, and if it's less than 5, then we will continue the cycle. Otherwise, we exit the cycle. So using that function, we're going to declare this 4-step process. So here we declare a FleCSI list, which contains a point for the initialized control point. It then contains a cycle, which is templated on cycle control, which says how to exit the cycle, and the 2 points that are dominated by that, advance and analyze. And then the final element of the list is the finalize point. So if we declare an action on this, let's say the initialize control point will have an initialize action. And in this example, it's just going to do an flog output of the string initialize. The way that the action gets associated with the control point is in this next line, where we say we have a control action. It takes the initialize function. It takes the initialize control point, CP : initialize, so it'll associate those. And this is a template declaration. It's associated with a variable initialize action, which we will not actually be using in this example. And if we do likewise for advance, analyze, and finalize, where we have a function for each of them, an action that we associate with the control point, and let's say that all of these functions simply output an appropriate string, then when you run it, it'll output with flog initialize, advance, analyze, advance, analyze, advance, analyze 5 times, and then finally it'll output the finalize. And you can also see what flog looks like, where it tells you where the message is coming from. We could define dependencies between actions. So here, let's say a new developer comes along and wants to declare a problem action. And what he cares about is that problem occurs after initialize. So here we have the bottom line here after we've created the action, where we add action to the initialize action. So that creates the dependency and says that problem has to run after initialize, but otherwise has no restrictions on when it executes. So I had mentioned the control policy. So everything's declared within a control policy, and you could add whatever data values and methods you want there. And those get passed to all these different other FleCSI routines. So once we have the control policy, we could create a fully qualified control type, as shown here, by passing it to FleCSI run control. And then the actions will be given this control policy and can use that for things like the field data, which is used by the application. FleCSI provides some convenience functions for doing graphical visualization. So given the control model, you could tell it to output just like shown on the left. So it produces GraphViz that you could run through a tool like Dot to get pictures as you see on the left. And it also has an option where you could say serialize this and show me an order that my actions might execute in, so you could get a better feel for a specific ordering. Okay, so that's the control model. Now we'll talk about more on launching FleCSI and the runtime system. So once the control model is implemented, we could run FleCSI on it. So this is similar to what we saw in the flog example. We declare the dependency guard, we declare a runtime object. Because we're using flog, we initialize flog by adding an output stream. And then to start the control model running, you call run.control, which is templated on the control model, and that starts running all of the actions in a partial ordering. For convenience, FleCSI also provides a way of adding program options to an application. So here's an example of that, where we declare a program option of type int. It's called mx and represents a mesh's x dimension. The arguments the user would type would be either --sizex or --sx for short. If the user requests help, it'll output the string specify the size of the mesh in the x dimension, and you could even have a default value if the user does not specify that, in this example, 10. And it's possible from the program to query these program options to see what values are set, if a value was provided, and other features. And with that, we're going to branch to the second hands-on exercise. In this, of course, you'll be learning how to use the control model. So we're going to take the application as it existed at the end of hands-on exercise 1. We're going to add a control model to that. We'll define actions, cycles, and dependencies. And then we'll update the runtime invocation to use this new FleCSI control model.